Connected by purpose, driven by passion. This is Children's Healthcare Canada's Spark Live webinar series.
Children's Healthcare Canada would like to thank the following Keystone funding partners for their ongoing contributions that support all of our programs and activities: the Stollery Children's Hospital Foundation, BC Children's Hospital Foundation, the Children's Hospital at London Health Sciences Centre, the Alberta Children's Hospital Foundation, the Children's Hospital of Eastern Ontario, and Holland Bloorview Kids Rehabilitation Hospital. We would also like to thank the organizations that provide funding for our knowledge translation activities, which includes this Spark Live webinar series, the Spark Conversations blog, and the Knowledge Exchange Network. To learn more about Children's Healthcare Canada, you can go to our website, follow us on Twitter or Facebook, or you can sign up for our weekly Spark newsletter at childrenshealthcarecanada.ca/email, where you will learn about upcoming events, read the latest posts from our blog, and other exciting news and events from across the child and youth healthcare community. Hello, everyone. I'm Doug Maynard, and welcome to Children's Healthcare Canada's Spark Live webinar series, where we curate, convene, and showcase excellence and innovation from across the child and youth healthcare community. And our goal is to spark conversation, spark ideas, and action. So welcome today in Ottawa. It's an extremely snowy day. I'm not sure if anyone in the Ottawa area is going to be listening to this from the hospital. Hopefully some of you made it there. Somebody's got to take care of the patients, but it's a good day to sit at home and listen to a webinar too if you weren't able to make it into the office. And since we are live, I do want to remind everyone that we do have the opportunity to type questions into a question box on your screen at any time. We may check for questions at any time throughout the session, so don't feel you need to wait until we ask for questions. Go ahead and type those questions in at any time that you think of them. And also feel free to share your thoughts on Twitter, and be sure to tag us at Child Health Can. All right, so today we're going to be talking about new approaches to precision public health and differential diagnosis using cognitive computing, AI, and big data. It's certainly a big topic, lots of technological sort of terminology there, but we've got a great presenter here today who's going to make it all, bring it maybe at least down to my level. I'm sure there's lots of you who are really eager to get into the nitty gritty on this topic, but Dr. Carolyn McGregor is joining us today. You may recall Dr. McGregor joined us at our conference a number of years ago to talk about her work in big data at Sick Kids in Toronto, working in the neonatal intensive care unit there, doing what she used to call, or maybe still calls, breath by breath and beat by beat data collecting big data sets from neonatal patients in their unit there. But Dr. McGregor is the Research Excellence Chair in Health Informatics and a two-time Canada Research Chair in Health Informatics, based at the University of Ontario Institute of Technology. Dr. McGregor has led pioneering research in big data analytics, artificial intelligence, Internet of Things, temporal data mining, patient journey modeling, and cloud computing. And now she's progressing this research within the context of critical care medicine, mental health, even astronaut health, and military and civilian tactical training. So lots of really cool and interesting things we're going to hear about today. So it's my pleasure to hand the virtual podium over to Dr. Carolyn McGregor. Over to you.
Thank you very much. And hopefully you can see my opening slide, correct?
Yes, we can, yeah.
All right, thank you. Well, good morning, everyone, and I'm truly delighted to have this opportunity to speak with this community about work that I've been doing in critical care and specifically with neonatology, and also speaking to you about the trends that this has and opportunities that this has provided, as was mentioned, to now extend my work into astronaut health, and I'll briefly touch on that at the end, and also with tactical operators. So I do want to say, as we move down through the slides, just having a technical issue that the slide progression isn't working. There we go. That my presentation, some of you will be familiar and used to perhaps photos of premature infants, but I'm also going to be having a couple of slides or photos about military law enforcement as well. So I just want to prepare the audience for that as a disclaimer. So moving on, many of you will have heard a number of technology terms. This is a very, very busy trend slide looking at the health technology innovation domain. And what I find interesting in this particular infographic is that the new areas have been corralled around these three broad themes: the top left of digital health, the bottom left precision health, and then over on the right with big data. Now, I'm going to be speaking about all of these different concepts today with some other terms, cognitive computing. For those of you who haven't been introduced to a number of these different terms, I'm going to be speaking to them, showing how they relate in the clinical setting, talking a little bit about what we're doing now and how this will change in working practices in the front line, how this will give you information in a new way and what we're trying to achieve. So interestingly for me, when I look at this infographic, it wasn't prepared by myself. The digital health, precision health and big data really is my focus area. As you'll see today, my discussion around big data isn't just looking at large data sets. My area isn't genome sequencing. My area is around medical sensors. So that's what we'll be looking at today. So I want to take a moment now and speak about this a concept of big data. It may have been a term that you've heard before. It is being used broadly these days in a lot of different contexts, as I mentioned, and you saw on that infographic. But I want to talk about a particular style of data that I've really focused on, which, as I said, is the data that comes from a range of different sensors and medical devices that you have in the clinical setting. And when the term big data was initially established, it was defined by some terminologies that started with V. Initially, there were three: volume, velocity, and variety. Veracity which was then added, and I'll explain these in a minute. You'll hear about lots of V's. There's 7 or 8 now that people have found of different words that start with V that you could use in this context. But I really just want to focus on these 4 to describe the type of data we're talking about. So this type of data has volume. When you think about the medical devices that are in the clinical setting and even now available in the home, data can arrive and be collected at a significant speed, and it means that we have lots of data on any given day. So if we capture something like heart rate and we capture it every second, we have 86,400 data points a day. If you think about an electrocardiogram, 500 or 1,000 readings a second, then automatically the order of magnitude is going up. The velocity itself speaks to the fact that this data is coming as a constant stream. We're not just looking at receiving those 86,400 points in a block on a daily basis. We are receiving it in a stream. And in my work, we deal with electrocardiogram. In our case, it's 500 readings a second. We're reading that in as it arrives and as it's generated. So that's what we mean by the velocity of data. It's actually the speed it's coming. And then the variety of the data. We have many, many different sources of data, just even within critical care. And in my work with astronauts, tactical operators and firefighters now, we have climatic conditions to consider, we have environmental other information, and information about what people are doing. In the clinical setting, it's important to understand when blood draws occur, even things like when diaper changes are happening with babies, because they can impact the signals that we get from the medical devices. So there's lots of different sources that we can receive this big data from. And it all can have, for the last one, the reason why I think it's important to include the veracity one as well, is that this talks about how reliable the data is or how much uncertainty that there is. For me, in the neonatal population, in a lot of cases, babies are left to sleep. So during those times, if there's very little disturbance with the senses, we can collect that data quite well. In other scenarios with movement, depending on the type of medical sensors or devices that are being used, sometimes that quality of signal isn't as high and it can impact what we're doing. So nonetheless, that gives you that broad overview of what we're talking about when we refer to big data. Now, some of the things that I also want you to be aware of is some trends in the overall environment of using computing tools to analyse this type of data. So there was some analysis performed by an organisation called Market and Markets, so looking at the use of data in the 21st century, and even in very recent studies, that Market and Markets have said that North America is going to dominate in the health analytics market, and the market is expected to grow to $18.7 billion, up from 5.8 billion in 2015 to 8.7 billion in 2020. So this is a significant focus area, certainly in Toronto with groups like Mars and other initiatives that we're part of as well, with the Vector Institute, for example. The growth area in analytics is certainly booming within Ontario and the Toronto region, broadly in Canada as well. And I draw on this other statistic. My area of taking data that's coming in stream, analysing it as it's being generated, is known as streaming analytics. And in North America, there's been some analysis of this streaming and analytic in and outside of the healthcare domain. And again, North America is quite strong, and there's some statistics on this slide. I won't read it all in detail, but it does show you, I'll draw your attention to the second bottom point, that the Canadian market has the fastest growth rate with a 30.1% CAGR, or compound annual growth rate. So we are going to see an increasing use. You may have heard this term Internet of Things, which I'll also get to in a moment. This is all to do with receiving this data from sensors and actually using it in real time. Previously, people have sort of collected it and then looked at it afterwards, and we're really trying to look at it in real time. So when I first started in this area in neonatology, there really weren't many sensors that people could use in the home and the community. It was really more focused in critical care settings, that we had the type of sensors that could emit this type of data. But now there's been quite an explosion of what we know as consumer devices. And I would like to draw the distinction between consumer devices and also devices that can be used in a hospital setting that are more medical grade, because there is a difference in terms of regulatory approval and also the quality of signal, and what you can understand about what signals you're receiving when. So a good example is something like the Fitbit, where you'll get intermittent readings, and it's not just that it's only a reading every hour. There are intermittent readings when the device itself, the communications and the analytics in the device feels that it's a quality signal, and it can report to you. But there's not a lot known publicly for a lot of these consumer devices about the quality of signal and reliability, which makes them a little questionable, and you have to be careful when you're using them in a medical context. But it certainly now presents in my work different opportunities of being able to take what I've been doing in critical care out into the community, which I'll speak to in the end. But first of all, I want to situate my work and motivate why it's really important to try and utilise these techniques to see how we can help by analysing in detail heart rate and breathing and blood oxygen and blood pressure, or any other information that's currently being collected by the sensors. So I just want to read through this scenario. This occurred at one of my collaborative sites. That an extremely preterm infant, day 10 of life, was ventilated and receiving parental nutrition via a central line. All the vital signs were stable and in the normal range. Settings on the ventilator were very stable. Blood gases were in the normal range. But the baby was noted to be lethargic on the morning of the ward round, some deterioration in respiratory status. Sepsis was suspected and antibiotics commenced. The blood work did confirm the clinical suspicion of sepsis, but unfortunately the baby deteriorated extremely rapidly, developed septic shock and died within 14 hours of clinical signs of illness. This happened in one of the partner hospitals that we are trying now to deploy my Artemis analytics platform for them to be integrated into our multi-site studies. Very tragic scenario that unfortunately still unfolds on a daily basis in many units. And what my hope is that we can use data that is showing on the screens of the bedside monitors and use it more effectively. So what we're looking at here is a baby who over a couple of hours has gone from being what they know as feeder and grower, one that just is being supported and observed, to one on the right who requires a lot of intervention for support. And can we take data that already exists, that already goes into monitors, that scrolls out of memory, and try and make better use of it? So that's been my focus for a number of years. So if you're not directly from this domain, just to provide a little bit of context, that there's a number of medical devices that surround a premature infant or an ill newborn infant who is in a neonatal intensive care unit. Their average on the, if I go around a clock face and we look on the top right at the heartbeats, we see an average of 130 beats a minute for the neonate, and that translates to about 7,800 readings per hour. And you think about the fact that on a traditional chart, usually only one heart rate value is being recorded. That's a lot of data that's being reduced down to one reading. Breathing is around 2,000 times they breathe every hour. We're measuring breathing behaviour at 125 signals or readings every 2 seconds. We're measuring the pattern of the heart rate around 500 readings a second. They're connected to infusion pumps for nutrition, for medication, a range of information. We've seen some infants that have up to 13 infusion pumps at the same time for those who are very sick. Blood oxygen saturation measured usually on a probe on a foot. Again, we have the plasmography waves that blood oxygen saturation calculations are derived from on a second-by-second basis. So we have 3,600 of those readings. And then if the baby is on a ventilator, again, there's all the settings from the ventilator. So very busy environment. And when you think about the fact that even with the electronic capture into an electronic health record that only one reading an hour goes across, I always felt, and the number of clinicians felt, that there was a lot of potential to see patterns in all of this data. So people ask me sometimes why I was focused on neonatology and not perhaps the over 65 cohort who present to critical care. These are some statistics from Ontario that of the top 10 by intervention healthcare interventions, so by not necessarily by quantity but by cost of individual care, out of the top 10, 5 of those are related to being born early. So we see this as a significant area for potential to assist, and this of course only counts costs to discharge. It doesn't count costs of lifelong implications of any morbidities that can be developed in this setting. And when I started on this work, many hospitals were recording those hourly readings on these paper charts and presenting challenges of significant data loss and even data captured in ways that couldn't be used. Even now, as I mentioned before, with electronic health records, the data now can go into these new electronic forms, but in many cases it's still downsampled samplings of data that really don't allow us to look for patterns in the actual data. When I started on the work, many of the hospitals around the turn of the millennium were transitioning from the medical device on the left to a medical device more like the one on the right. And even now, when I think of it today, many hospitals have had the devices that look more like the one on the right for 15 years, and some of them even 20 years now. On the left to the right, there was a technological advancement of going from an analog signal to a digital signal. But as I've said to many at the bedside, that didn't really change the opportunity for care. And the one on the right has colour. But again, providing colour as opposed to a single colour or different colours as opposed to a single still presents those who are at the bedside with a whole lot of numbers that flash up on the screen that don't really speak to trends and patterns and behaviours that can be seen in the data. So my work focuses on looking at how we can potentially utilise that data to help support the differential diagnosis function. And I think it's an important distinction that my goal has not been to think about, can I come up with something to replace doctors or nurses? My goal has been the challenge of what has often been presented to be by many doctors in many countries is that when a patient becomes unwell, the differential diagnosis set is just too broad. There are so many things that it could be. They don't have enough tools and techniques to try and narrow that focus. So that has been one of the key drivers of what I do. And I want to speak a little bit now about what that means, thinking about the fact that what we're trying to help with is a differential diagnosis step. I want to introduce, if these are new terms to you, the idea of cognitive computing and artificial intelligence. So the term cognitive computing means that we are trying to use different types of computing techniques to mimic the way that the brain works. So the decision-making paths that someone would make at the bedside, trying to receive signals and understand what they mean, and then trying to use some other methods of testing to try and help to reduce that, we're trying to provide a way that every breath and every heartbeat, every blood oxygen saturation, as well as other readings, can have some analysis performed on it, which is too much for a human brain to do, particularly when there's so many patients in a critical care unit. And we're also trying to use what's known as some artificial intelligence techniques. So these are particular types of computing techniques that are trying to discover patterns in data. So the way that some of these techniques, some of the terms you may have heard, which is data mining, which is where we're trying to perform different ways to cluster and group data and understand patterns in the actual data. You may have heard the term pattern recognition, which is again a similar term. You may have also heard the term natural language processing, where we're trying to turn naturally constructed language sentences and look for really the themes of what the sentence is trying to portray, and then to utilize that information as data that can be analysed. So that's just a little bit of a backdrop. So what we're trying to do is look at ways that we can use this type of data in ways that's much more complex, and that needs to be done at a speed that a human brain can't do at that complexity and at that speed. And so another way of looking at it that you might also have heard of is personalised or precision medicine, where we try and construct these models. So mathematical models could be looking at biodata, they could be looking at other forms of data as in what I'm doing. And the goal is to try and construct something that is more precise, that use much larger patient data sets, and creates a way for more effective interventions that are for that individual. A lot of work previously has been done based on populations. And so we can tailor the healthcare, anticipate responses, and work with individuals. And so that's really what a lot of these terms mean. So apologies if you already knew that, but I envisage that there's some in this audience who aren't familiar with those terms. So one of the things that I noticed when I started looking at this area of how can we use computing and analysing data to support medical decision-making, I looked at the way that these signals of heart rate and breathing were being analysed. And I noticed that people would analyse them retrospectively. So they'd gather a whole lot of data, go away from the bedside next week, next month, and start looking at it. When they found a pattern that had a potential, they didn't have any mechanism to implement it into clinical practice. It certainly wasn't scalable if they could find a way. And a lot of the studies either were trying to say, we want a way to understand if a patient is becoming unstable, or we want a way that we can detect infection earlier, or we want a way to understand if something's changing in the heart rate. There really wasn't flexibility to build a combined system to do everything. And the focus on a lot of occasions has been, what new box can we put at the bedside? And trying to put a whole lot of more technology in a box at a bedside, instead of looking at how we can use software that doesn't necessarily have to be located in the box at the bedside, but that we can send signals out for a lot more complex analysis. And so I want to just move on now to some of my initial work that we had in looking at the current state of analysing infection. So one of the things that we did want to go after initially was this challenge of detecting infection, because it can be so devastating, as I mentioned before, particularly in a neonatal population. And this diagram was a great analogy that I became aware of, and a lot of cases the neonatologists and other healthcare professionals in the neonatal units hadn't really thought of previously. So the vials on the left-hand side reflect the amount of blood volume that a neonate has, particularly if they're born very premature. So it represents 40 mils of blood, because a human has 80 mils of blood per kilo. So they only have about 40 mils of blood. The ones on the right are representing 2 mils of blood, which is drawn when the baby is suspected of having an infection. Now, if the baby actually does or is diagnosed with infection, 2 days later they need to draw another 2 mL of blood. Now, this is just a diagnostic test for infection. If there are other things, they may need to draw more blood. So we've taken 5 or 10% now of the blood volume, and a newborn can't start generating blood for 1 to 2 months. So then we have to start, or the clinicians have to infusing blood to be able to provide the blood back to the infant. So we really have the opportunity to look at ways of, are there other ways that we can detect that this is happening and potentially detect them more accurately. So what I wanted to do with the Artemis platform, which I've created, which is named after the Greek goddess of childbearing, I wanted to be able to capture the data that's already existing at the bedside and see if we can analyze it and use it and create more of an analytics platform rather than just showing numbers of signals all the time. So that's been my goal. So I won't dwell on this. It is a technology architecture, but I just want to explain in principle the way Artemis works. So we receive data in the top left from the different medical devices, go through a mechanism when we can acquire the data. People often ask me, what does Artemis look like in the hospital? And I said, well, actually, it's usually a purple cable or a blue cable. That's literally how you can see the way the data is being captured. It just connects to the back of these medical monitors where the data can come out of those devices, so we can then feed it into the system. Goes through the network to wherever the Artemis was located. Initially at Sick Kids, we had an in-house Artemis installment as our first deployment there, and you'll see later that we now run in the cloud, and I'll explain that in a minute if you haven't heard that term before. But the data feeds ultimately into the online analytics platform. We separate the signals. We use them concurrently for lots of different algorithms. You'll see in a minute all the different things we've been looking at. We can store the data. We come up with summary analytics. We store that as well. We can include all of that data. I have a data mining or an artificial intelligence technique down the bottom middle where I talk about knowledge extraction, that we can look at all of these patterns of the data as streams of data, look at what associates with what medical conditions. I'll explain some of our examples of that in a minute. And following traditional medical scientific method null hypothesis testing based research, if we find that patterns do correlate with certain conditions, we can deploy those new algorithms into the environment, which is what we've been doing. And then obviously on the right hand side we can present the results of the bed space. So what we're looking at and what you will see as we move forward, and the next type of intervention you'll see at the bed space is rather than just seeing all of these numbers all the time, you'll see things being more correlated with conditions, which is what we're trying to look at now. So this is a graphic of some of the early work that we did in late onset neonatal sepsis. It represents an hourly scoring, so each bar represents an hour score of how stable we see the patient or the infant in this case. So you'll see that it's almost 3,600 readings. It's because the device we use, it's almost a reading every second, so we can derive a score. The dark blue of a score of 0 means that there's no abnormalities in any of the signals. The light blue means that heart rate is showing an abnormality. Yellow, it's heart rate and respiration. Pink, heart rate, respiration, blood oxygen, and red, all of those, and blood pressure. So you'll see hour upon hour there's a significant trend change around 20 hours or maybe 15 hours in from the right-hand side. The colours start to change. Now, if I was to tell you that the second hour in from the right-hand side was at the bed space when they suspected LONS, or late onset neonatal sepsis, and they ordered the blood work then and started antibiotics. So you can see then that this technique has potential and that we knew there were changes in the signals. Unfortunately, with this technique, though, there's so much information, it really didn't tell us which aspects, which behaviour of heart rate and breathing are the ones that really... Yeah. So this slide demonstrates around the same time, we actually had interest from a hospital in the United States, Women and Infants Hospital in Providence, Long Island, to join the research. And they were interested in the idea of not deploying something locally in the hospital, but actually deploying it outside and for us to be able to provide these analytics as a service. So we were able to run a study where we captured the data from the medical device is in the hospital and sent the signal to Canada, and we're doing the analytics here. So these changes, so we're working in parallel with coming up with algorithms for the bedside use and looking at, from a technology perspective, how we could provision this in the longer term. So hopefully everything's working along and I can continue. That study allowed us to see that we were able to offer this type of approach by running it from outside the hospital. We enrolled 203 patients. It was 10.6 patient years worth of data. And interestingly, even at a spot reading every minute as the speed which we were limited to just from the medical devices, we were able to show that the Artemis platform running in this way was 100% service, or had 100% service availability, and that network failure, like we were just experiencing, had resulted only in a data loss of 0.1%. Because as you'll see with the way that we do this, we can buffer the data in the hospital and then send it through. So moving on to the next slide. So getting back to the clinical focus, one of the things we started to try and tease out was for every signal that we had, what were the patterns we could start to see. So this is a heart rate and respiration rate variability score on an hourly basis. And what we found was that babies who are in more of that feeder and grower state, that these scores stayed on an hourly basis between 10 and 40 out of a score of 60. But then for a baby who had surgery and had fentanyl or midazolam or morphine, the variability in the heart rate and respiration was severely impacted by those drugs. And that's what you can see in the bottom diagram in the first section to the left, that the scores are closer to 60. As those drugs are being expelled from the body, you'll notice that the respiration rate, which is sort of in the dotted line across the bottom, returns down to that 10 to 40 range, but the heart rate variability didn't follow that same recovery pattern. Now, this is actually the signal from a baby who went on to develop sepsis post-surgery. So we started to understand what we could see in individual signals and what it was about those signals. And others were discovering as well that we could find these things. And it's really a matter of realizing that sometimes heart rate variability is reduced from one thing or another. Now, what I have here is some other work that we went on to do to understand the pharmacokinetic and pharmacodynamic behavior of morphine and understanding how that was reflected in the heart rate variability signals. So taking that concept we saw from post-surgery and what we could see in the population. Now, what I want you to take from these diagrams, the main finding that we found in this research was that we could see correlations in the way the heart rate variability changed in dosages of morphine for the children who are older, for the children who are heavier. And they're the ones you can see reflected with the black dots on the surface. The dots on that are green, that are off to the side of the surface, that are for the very small, for the very premature, they don't fit. So that tells us that we're not seeing the same behavior of the way morphine is interacting in the body and the changes it's making to the heart rate signals in those younger infants. So that was an interesting finding when we were looking at the pattern in the data. This is another interesting pattern that we found within the data that led us to understand the correlation in heart rate variability with anemia and the need for a blood transfusion. So we started to look in detail when we had reductions in heart rate variability and trying to understand patient state at that time. This is important for that differential diagnosis piece because we want to understand if we're seeing changes in the baby's state, that we can help to try and say, well, the pattern is more like an anemia pattern, or the pattern is more like a drug pattern, or the pattern is more like a late onset neonatal sepsis pattern. I want to draw your attention to roughly 2/3 across the slide. I'm not sure whether you can see where my cursor moves to, but I want you to draw your attention. If you look at a line of best fit in the blue graph, which is heart rate, the line of best fit initially from left to right runs through at about 30. And then you'll see a time where my cursor is, you'll see a 19 on the timing score across the bottom. And you'll see that there is a significant shift in the heart rate variability, and then it is much lower with a line of best fit more around 20. So we investigated what happened at that moment where there was that significant change, and we found out that was a blood transfusion. You'll also note to the left of that there's a significant rise of the respiration, or reduction really, in the respiration rate variability, and also in the heart rate variability, and that was a bolus, so an intensive drug infusion at that point that caused that reduction in both heart rate variability and respiration rate variability. So what we did with this knowledge then, getting back to the transfusion, was that we then extracted information for a number of babies we'd previously collected data on and looked in detail at the transfusion profile. And we found this next one shows we averaged pre and post the blood transfusion timeline. You'll see where blood's mentioned in the middle of the chart. And you'll see overall there is a higher score of heart rate variability indicating a reduction, and then a lower score afterwards. So we're doing more work in understanding now the behaviours that we can see in the need of a blood transfusion by looking at heart rate variability. So moving on to some further studies, in addition to just looking at what we can see in blood in the heart rate behaviour, we wanted to look at the interplay of lots of different signals. And one of the areas this is critically important is understanding when a baby's becoming well. There's a general collective term known as a neonatal spell. That means that there is some sort of unacceptable threshold breaching in either the heart rate, the respiration, or the blood oxygen saturation. They can happen in different orders, they can mean different things. It's very difficult for a human at the bedside to try and annotate what happened first, and usually the devices only have fixed thresholds instead of having movable thresholds. So, or thresholds that relate to relative distances. So on the right-hand side, 10% changes in baseline, or a two breath distance, rather than the fixed thresholds on the right. I want to draw your attention to, on the chart here, of the respiration pause. You can see that in the imp wave, or the impedance wave, you'll see the flat line underneath where it says respiratory pause. Following that, you'll ultimately see a fall in the SaO2, which is blood oxygen saturation. So one happened and then the other. And so what we're interested in doing is not only tagging when certain patterns happen in the data, but the interplay and the sequence of them. So some of the work we've done is looking at, on this next slide, the type of spell behaviour it is. And then on the right, the order that things need to happen in terms of when there is a problem, and also the recovery pathway. So we've been able to do some work analysing and annotating this in real time by using this approach of analysing big data. Just quickly, because with the network interruption, I just want to make sure we have time with questions as well. Many of you will know Stevie Wonders is blind. You may not know that the reason he's blind, he was born premature. He had oxygen therapy as a preterm infant, which damaged his developing retina. And it's still a problem that exists today. And I want to draw your attention to why looking at every single reading is really important. So a lot of the work in understanding blood oxygen saturation ranges is done based on the first reading of every hour. So this chart shows for one infant for one day, 12 hours on the left for day shift, 12 hours on the right, and whether they're in the target range, below the target range, or above. Now that's just taking the first reading every hour. The bottom chart is taking every single reading in the hour, and it does present a very different picture about really what's happening. This is why it's really important for us now to utilise these new computing systems to look at as much data as we can, because it helps to create a proper picture of what's happening. So the types of things that we can deploy at the bedside is to show hour upon hour how much of the baby was in the target range of oxygen. And interestingly, in an initial study that we have performed looking at this, we found that in our population, it's the variance of low and high and not just high oxygen that is occurring in the population who went on to develop retinopathy prematurity. Now, that is only early results. We're looking to analyse that in more detail. And it shows the potential of what we can see when we look at more data. Just quickly, also drawing your attention to the fact that we have been able to do work to automatically annotate brain signal monitoring to be able to annotate sleep and wake cycling. You'll see from the note at the bottom of the screen, we can look at the features in the wave from the CFM to be able to detect that. And so that's shown you a number of the different clinical investigations that we've been pursuing by utilising this type of data. For those who are more technically inclined in the audience, this shows the progression of actually creating a platform to be able to do this. So the initial Artemis platform, or the actual platform itself, was deployed in 2009 after work started on it more formally in this form in 2008. Cloud version with Women and Infants Hospital deployed in 2010. We deployed an initial instance of Artemis at the Children's Hospital of Fudan University in 2012. We also tested the cloud-based approach. Interestingly, in that setting, we had more challenges with the signal with the network getting it to the edge of the hospital than we did once we could get it from the edge of the hospital all the way across to Canada. Apollo, home-based monitoring, I'll touch on that in a moment. And then I've really been working on commercialising a platform that can receive data and support multiple hospitals, which is that Artemis Cloud expansion. We now are running live to collect and run analytics at 2 hospitals in Ontario, 68 bed spaces. So those bed spaces, the data from the bedside is streaming live, has been for over a year. We have some initial study results coming out from that work, both in terms of system availability, but also more importantly what we're finding in relation to our late onset neonatal sepsis study. So watch out for those new papers coming out and reporting on those results. And we are also now working on deployments in India for a low resource setting model, and also a partner companion architecture approach in Australia. So just in terms of speed, just for those more technical in the audience, I'll just give a quick overview here. So we take in the top left data from the number of medical devices. We have to go through what's called a serial to Ethernet conversion. Many of the devices, it's not an internet signal that the device manufacturers have enabled. We have to do some conversion work to get the data out. We de-identify patients. I think it's important to know our protocol is that we go through a de-identification process for security and privacy before data leaves the hospital. So it's study identifier or alternate patient identifiers when it comes out of the hospital to come to our analytics platform, and we have the mechanism to re-identify the data when it comes back in. And then I'll show on the next slide really what's happening. So 2 hospitals online, McMaster Children's Hospital in Hamilton, South Lake Regional Health Centre in Newmarket. Both of those hospitals were acquiring, as I said, from the neonatal units, sending data live through the Orion network all the way across to Queen's University. We're using infrastructure provisioned at the Centre for Advanced Computing through a Compute Ontario initiative to run my Artemis platform there 24/7. It's an unusual case of cloud computing, first of its kind in the province and the country, because we are streaming data live and running analytics live. So again, just if you're interested, the speeds of the data, we have 500 readings a second for electrocardiogram, 62.5 per second or 125 every 2 seconds for respiratory or chest wall movement. The blood oxygen plasmography, again, 125 readings every 2 seconds, and the same with the blood pressure, and then a whole lot of derived readings like heart rate, respiration, blood oxygen every second. All of that data is coming across and being analysed in real time. So as part of the babies who are in our study cohort, there was a baby who was noted to have a small amount of blood in their mouth. 5.5 hours later, the baby was noted to be pale. 20 minutes later, a culture was taken, and 15 minutes after that, they were in septic shock, sedated, intubated, fentanyl, atropine, etc., and ventilated. And 30 minutes later, they started the antibiotics. We've captured the data for this baby as a positive LONS case. this will be part of our study results. We'll be reporting very soon about using this type of intervention at the bed space and the potential. This was running in parallel. Our next phase coming soon is that we'll allow analytics, or we'll run studies to show analytics at the bedside. So our goal is to avoid this situation, as was in the case of the 2 babies I've spoken about. So I've already mentioned this, and I'm going to whiz through so we have time for questions, that in Australia we have similar tyranny of distance issues, because I am Australian, if you've been trying to pick my accent. I draw your attention to Perth on the of Western Australia. You'll see a town of Derby. It's a similar distance that from those in Ottawa who do the extractions from Baffin Island. It's that same sort of distance in Australia as it is to Canada. So we have these large areas. We're looking at deploying this type of analytics, and the reason also for this cloud-based deployment is so that we can get this technology out into rural and remote communities and understand patient state, so that we're not dealing with very critical patients by the time consults come in for transport. And this idea of the radio doctor or telehealth, many people think that it's only in the last 10 to 15 years, but this article is from a magazine in 1924. Through the joys of the internet, you can actually find this particular article and read it. The technology would have worked, interestingly, at the time, and we're still only now starting to get systems in place beyond just video conferencing, where we can send live streams of the medical data. So quickly, we've performed this work in the home with neonatal graduates going home with monitors and being able to continue to monitor them in the home. So parents aren't trying to just come to terms on their own with looking at raw data signals. They're on a second-by-second basis. So watch for that sort of work coming in the future. And as I mentioned, and I will just provide a bit of a teaser really of some of the other work so that I have time for questions, but I had the opportunity to speak to a staff sergeant of a tactical response team about the work that I do, and he said, well, that's interesting because we really need to understand the physiology of the tactical operators when they go into a school or a shopping mall, and they're trying to contain an active shooter. Because if their physiology, if their heart rate gets too high, if they have issues with their breathing, it impacts their blood oxygen saturation, they can have tunnel vision, they can pass out themselves. So I've been working on systems that we can build to allow tactical operators while they train to understand how their own physiology is behaving. And I actually also now work with tactical operator community, firefighter community, and as we alluded to in the beginning, I also have strategic projects now to have this work as part of the mission to Mars for autonomous health monitoring of astronauts in space, been part of some analog missions on Earth isolation experiments in the Russian isolation facilities that we use for the Mars 500 project, so that we can help to look at real-time systems. So finally, because I'm now working in all of these different populations, we're starting to see trends of how this can lead to new precision public health initiatives, looking at how we can deploy these types of systems more systemically for individuals and population groups with the goal of improving health outcomes. And we're doing transdisciplinary work now around the broad areas of resilience and adaptation, and looking at just those concepts with general health and how some of the work from the tactical operators can help with the space work, and the space work can help with adaptation with the babies. So some very interesting future directions in that area. So I want to take the opportunity to thank all my clinical partners in all the different neonatal units around the world. My partner in research, who is the gentleman in the top right, Roman Baevsky, who has been working with the Russian space program since they first deployed the first human into space, and all of my other clinical partners. The industry partners I have, couldn't do this work without them. Funding from a range of countries around the world for all that we do. If you want to follow my work, please feel free to do so with my team's Twitter account, UOIT Health Informatics Research, or HIR, and my own Twitter information there. So I'll leave that there in case you want to make note of that while I open it up now for any questions.
All right. Well, thank you very much for that presentation. I mean, just mind-blowing, some of the stuff you're doing. It's really quite incredible. Not just the work you're doing in healthcare, but when you start applying that, like just the creative applications to the tactical and the space program is really quite amazing. So congratulations on that great work. We did have a question, and so this is just remind the audience, this is your chance to ask any questions that you would like. We did have a question that came in when you were talking about, the data collection and the building of mathematical models around to represent these patients, et cetera. And just wondering what type of mathematical modeling you're doing, just even if it's just at a high level, to just give us some sense around that. Are you talking about, they were asking if it's possibly ordinary differential equations, longitudinal analysis, or some other type of model? Mm-hmm. And do you believe that this can be used for predictive analysis?
Yes. So yes, and all of the above. So we have to use a range of different techniques incrementally. So we do use differential analysis. You may have heard the term deep learning. That's a common phrase that's being touted now. It is a concept that we've been doing for some time. What we have to do is create building blocks. So we have to build knowledge layers up in the data. So in our work, we have to look at what we see in terms of patterns in the data itself for an individual patient. Then we have to take those individual patterns and look to see whether we see those same style of patterns in the data for other infants and correlate that with certain events that are happening with them. So a good example of that is with the blood transfusion work. So we're taking the event of the blood transfusion and we're looking at the relative distance and then looking at going back 24 hours from that point, what patterns that we see in the data. So when you were looking at the tracings for the blood transfusion example, it wasn't the raw heart rate. It was looking at what we've derived from heart rate variability. So we're using a range of techniques. One of the things that drove this initial research was a data mining concept called cluster analysis. So we were looking at broadly in the population when we saw heart rate variability scores reducing. And then we were trying to cluster babies that had the same style of heart rate variability reduction. That allowed us to see this pattern that was different, which was the blood transfusion pattern. It allowed us to see the very different pattern of when there was virtually no variability at all, which proved to be the medication pattern. And so we are utilizing a number of different aspects. My core discipline is data science. So we really are not leaving aside any method of mathematical technique that we know, and we're creating new ones ourselves as well, because we just have the opportunity to do so much exploration.
It's an interesting sort of, especially in healthcare, it seems that it's a bit of a different world. Some of these technologies are, especially around big data and artificial intelligence, et cetera, being used, extensively in many other industries, in the technology sector in particular. Mm-hmm. And it just seems to be such a challenge in healthcare, where there's so much of especially people who have been in healthcare for many years, there's so much of an emphasis put on the human element. So, for example, I can just hear, as you're talking about, you give the blood transfusion and then you can see these changes in heart rate variability, et cetera, that suggest that the patient is now doing better. Where you get the nurse who's been at the bedside for 20 years and says, well, I can tell you just by looking at them that the patient's better after giving the blood transfusion, or that things settle out or whatever, like that they can visibly see that. And it's my experience as a practitioner for 20 years that tells me that I don't need your technology. Is that like, can you describe whether that's a valid observation? Is that a barrier to this kind of technology?
Oh, absolutely. So there's some really key things that people need to understand, whether you're in or outside healthcare, and why it's different when we implement in healthcare. So I'll speak to the three areas that have come up, just what I think of what you were saying. So first of all, a lot of the approaches with this using data analysis to bring it to healthcare has been these what we call black box approaches. Now, there are artificial intelligence techniques where they just leave it internally to try and cluster patients and then learn from that and then take in the new patient and say, well, it's one of these. But that's called a black box approach, because you actually don't understand the features it's finding in the data, but it's just telling you, well, I've got this accuracy. And so the doctors themselves and any healthcare professional are being asked to be liable to take on that responsibility. So, and to just assume that the black box is correct. Now, in my work, I'm actually much more interested in what's called a white box approach, which means that we use the strength and the power of computing tools to actually learn what the patterns are, to demonstrate through, as I said, through full visibility, this is the performance of the patterns and these are the patterns we're looking for. And it allows clinicians to apply their own thinking and knowledge to that scenario. The second point that I want to make, and this is an analogy I use all the time, that Walmart, when they started to use data mining techniques, found an interesting pattern that on a Friday afternoon they found that diaper purchases were highly correlated with beer, as in alcohol. Yes, you can think about what might be happening in these scenarios. So no, they didn't move diapers into the alcohol section. They moved alcohol, pallets of beer into the diaper aisle. So when, and I'm being very stereotypical here, but if there's the call in, can you pick up diapers on the way or can you go out and do the run for diapers, that they went to the diaper aisle, saw the beer, realised that it was the weekend and bought the beer as well. Now, if that strategy hadn't worked, Walmart just moves the pallet of beer back. If the strategy doesn't work in healthcare, we can kill people. So we really have to be very clear about using traditional scientific method null hypothesis techniques to test the patterns we find, to prove two things. Are these trends really correlating with the condition? And are they a predictor on their own of the condition? Or are we going to have false positives because there's actually other conditions associated as well? So they're two key trends that we need to look at. And your example of a well-trained nurse at the bed space, absolutely. We know that often it is a well-trained nurse still who has the best indication of what's happening with the baby. What we're trying to do is or to provide the information for is that blood transfusions don't always work. And we're trying to understand patterns where they're likely to work and not as likely to work. And so that's where we're trying to really learn in reality what the nurse is actually seeing and quantifying some of those behaviour traits and finding out what it is about those patterns. So I hope that's answered your question.
I think that's a great answer. I think, it's one thing to have that like you said, that well-trained nurse at the bed. We don't always have that well-trained nurse. Some nurses are newer and don't have the experience and don't have, that sort of experience to know those things or that intuition. And, this kind of technology ideally would give everybody that support so every practitioner can have those observations and those insights. So
absolutely.
I'm curious, so when we look at all of the different components that come together to make this kind of technology possible and to get it into the bedside and really start applying it to everyday clinical decision making, I mean, it's an issue of having the right technology, it's data collection, it's some of the culture issues of the various professions that we just talked about. Privacy of sharing data is always a huge issue within Canada. If you had to pick one of those issues, like what would you say is the biggest barrier to implementing this in clinical care in Canadian hospitals?
Procurement of medical devices that don't allow data to be collected. Because if we can't get to the data, we cannot do anything. All the rest of it we can overcome. But if healthcare facilities procure devices that don't allow data to be collected, we never even get a chance.
That seems like it should be easy enough to overcome as well. But so it's really just an issue of working with vendors to have better data collection from their devices.
Mm-hmm. All the rest of it is about showing potential, demonstrating reliability, demonstrating performance, showing the change in outcomes. All of that can flow on. We've had so many challenges with medical devices that hospitals have at the moment, and changing procurement cycles and approaches to ensure that there are open ways of extracting the data out.
Well, for, say, someone like Canada Health Info in building those standards that could then become regulations that would require vendors that sell devices in Canada to have that kind of interoperability, et cetera, et cetera. I mean, that seems like it might be a role for InfoA. I'm not 100% sure if they get involved in devices in that sense, but is that a role?
Yeah, and there's also there's an electrical engineering body, a professional association body that I'm part of. It's called IEEE or IEEE. They are the ones who actually propose a lot of standards. So there's a new standard that's recently been released. It has a number. It's 11073. It's Health Data Interchange Standard. There are a couple of different standards still, but this one is the one now that they're trying to centralise around. There would be a lot of problems solved if hospitals and healthcare facilities, when they're going through the procurement process, put pressure back on the vendors to say, we can't purchase equipment from you unless you utilise a standard, or it's certainly a very open and visible protocol that the data is coming out of your device with.
And interesting, I was not expecting that to be the response. I was thinking the technology was there and just ready and waiting for us to embrace, but it's really still bits and pieces with the technology that we're dealing with before we get there. So I think we've gone over time a little bit. I think that's all the time we have for questions. I'll just hand it back over to you, just if you have any closing comments, key messages, what's next in your research, where can they find out more, just anything you'd like to leave the audience with before we wrap up for today.
Certainly. So if you would like more of what we're doing, both in critical care with the astronauts or tactical operators, firefighters, please do watch for our updates on Twitter. We are looking to show how this can be used for resilience to help prevent post-traumatic stress disorder in space for the mission to Mars, as well as bringing it all down to Earth locally and in rural and remote centres. So I hope you found it interesting to find out what we're doing, and thank you very much for your time.
Again, great presentation, really gives us lots of things to think about going forward. So thanks again to the audience for joining us today, and for you such a great presentation.
Thank you.
We do our webinars every Wednesday at 11 a.m. Eastern time, and when you do get to watch live, you do get to ask your questions and contribute to the discussion, which is great. But when you can't watch live, the recordings of these sessions are made available after the fact on our Knowledge Exchange network. Our next webinar will be on February 20th, and we'll focus on patients' perceptions of physician wellness and its links to patient care. And this will be a qualitative study done by Alicia Polachek from the University of Calgary. And this presentation is going to focus on a study of 20 patients regarding their perceptions of physician wellness, and how their perception of wellness affected their ability to care for them as patients. The study was done on adults, but we're going to really be trying to make the links to children and the pediatric world as we go through this conversation. So it's going to be an interesting discussion, and perhaps there'll be an opportunity, similarly to the tactical squads, for physicians and other healthcare providers to be wearing those sensors, and we can learn more about their performance through physiological data collection, perhaps at some point in the future. So thanks again for joining us today, and hopefully we'll see everyone back here next week. Bye, everyone.